Okay guys, let's start with a little bit of review. We're going to go into a unit called sequences and series, and first we just want to talk about sequences, and after this lesson we'll talk about series, but right now we're going to talk about sequences. And to start sequences we need to be able to write sequences, so let's do these review questions. The first thing we're going to talk about is, okay, if you want to write the first 5 terms of this sequence, okay, this sequence is named A sub n, what are the first 5 terms? So what you would say is, you'll say the first blank is n equals 1, the second blank is n equals 2, the third blank is n equals 3, and so on. All right, and we're going to fill in these blanks. So if n is equal to 1, the first blank would be 3 times 1 over 1 factorial. 1 factorial is just 1, so this would be 3 in this blank. Right here you'd have 3 times 2 over 2 factorial. 2 factorial is 2 times 1, so this would be 6 divided by 2, which is 3 in this blank. In this blank here, we're going to have 3, so that would be 3 times 3 over 3 factorial. 3 times 3 is 9, 3 factorial is 6. 3 factorial is really 3 times 2 times 1, so let me write that down. Maybe this will be helpful. And so this blank here is 3 halves. I'm going to move these blanks over. All right, for the n equals 4 blank, let's go ahead and put in 4 for the n. So this would be 3 times 4 over 4 factorial, but 4 factorial is 4 times 3 times 2 times 1. The 4's cancel out to 1, the 3's cancel out to 1, so what I have here is 1 over 2. And then finally, when n is equal to 5, what I have is 3 times 5 over 5 factorial, but 5 factorial is 5 times 4 times 3 times 2 times 1. So the 5's will cancel out to 1, the 3's will cancel out to 1. So what I have here is 1, 8. All right. So let's look at the first 5 terms of the sequence. This answer will be 3, 3, 3 halves, 1 half, 1 eighth. And those are the first 5 terms of the sequence. Notice what sequences have. Sequences have commas in between. All right, so that's super important to note, because later on when we get confused with series, series have plus signs in between, okay, which means something completely different. All right, let's look at the second problem here, or the first 5 terms of this sequence. All right, again, we put blanks, n equals 1, n equals 2, n equals 3, n equals 4, and n equals 5. All right, if n is equal to 1, that'll be negative 1 raised to the 1 power over 1, so this first blank is negative 1. If n is equal to 2, what I have is negative 1 raised to the second power over 2. This is going to be negative 1 times negative 1, so this will be a positive number. When I have n equals 3, the top number is going to be a negative number, so this will be negative 1/3. If I have n equals 4, I'll have 1/4 here, and if I have n equals 5, I'll have negative 1 over 5. All right, so let me go ahead and write these terms to make sure we're on the same page here. The first 5 terms of this sequence here are going to be negative 1, comma, 1 half, comma, negative 1/3, comma, 1/4, comma, negative 1/5. What's interesting is what this n does here is it changes the sign for each subsequent a sub n. All right, so that is the sequence. Again, notice sequences have commas in between and not plus signs. All right, let's evaluate this here. 7 factorial over 5 factorial. Make sure you understand how to do this. 7 factorial is really 7 times 6 times 5 times 4 times 3 times 2 times 1. 5 factorial is really 5 times 4 times 3 times 2 times 1. And these factors will cancel out, so the answer here is 42. All right, let's see if we can do this problem here. This says evaluate this limit. Well, before we try to do the limit problem, let's just look at the fraction here. The fraction here is n plus 1 times The next term less than n plus 1 would be n plus 1 minus 1, right? So that's going to be n. So what I have here is n, and then n minus 1, and then n minus 2, etc., right? On the bottom, I have n factorial, but what is n factorial? Isn't n factorial really just this part right here? N factorial is n times 1 minus that, n minus 1, times 1 minus that, n minus 2, and so on. And so for this problem here, these terms actually cancel out. So what I have is the limit as n goes to infinity of n plus 1. All right? And what is the limit of that? There is no limit, okay? This limit diverges, or you could say is equal to infinity, or you could say is equal to dne. All right, and we can kind of show that if we wanted to plug things in here. So what would happen if I try to plug things in here? Let me see. Let me pull this down. If I plugged in some numbers in here, let's say I plugged in 1, I'll get 1 plus 1 over 1 factorial. If I plugged in 2, I would get 2 plus, oops, this is 1 plus 1 factorial over 1 factorial. This would be 2 plus 1 factorial over 2 factorial. 3 plus 1 factorial over 3 factorial, and oops, comma, and so on. So what is this? This is 2 factorial, comma, 3 factorial over 2 factorial, comma, 4 factorial over 3 factorial, and you can kind of see the pattern. This would be 5 factorial over 4 factorial, 6 factorial over 5 factorial, etc. So this would be 2, comma, 3, comma, 4, comma, 5, comma, 6, comma, and what's going to happen here? This approaches infinity, right? This increases without bound. All right, the answer here is infinity. All right, let's go on to sequences now. You should have these notes that you can follow along. These guided notes were made by Nancy Stevenson, an AP teacher who teaches a lot of the AP institutes. And this is her guided notes, which are great. So let's go ahead and go through them to learn sequences. All right, what you need to know is a sequence is a function whose domain is a set of positive integers. So its domain is 1, 2, 3, and that's how we substitute the n. The n is the domain. All right, the range is the a sub n. Okay, and the subscript n is usually understood to start with 1. Sometimes it doesn't, but if there's no expression otherwise, okay, if it's not explicit otherwise, then n starts with 1, and it includes all the positive integers. All right, so 1, 2, 3, 4, 5, so on. All right, let's look at this sequence here, 3, 8, 13, 18. The formula for each of these n's, this a sub n, is equal to 5n minus 2. All right, and so that means if I said this was n equals 1, if I substituted 3 here, okay, I'm sorry, if I substituted 1 here, I would get 3. If I substituted 2 here for the n, I would get 8, and so on. We did that in the warm-up. All right, this is called an arithmetic sequence. The reason is because to get the subsequent term, you do the same thing. You add the same number to get the subsequent term. All right, the common difference is 5, so we call that d is equal to 5. And in pre-calculus that you learned that if you wanted to find this formula, 5n minus 2, that formula for a sub n is equal to the first term, a sub 1, which is this right here, 3, plus d times n minus 1. All right, and that would work for this. So like for this, if you didn't know this 5n minus 2, you would say, okay, a sub n for this sequence is equal to the first term, which is 3, plus the difference, which is 5, times n minus 1. And if you manipulated this around, you would actually get 5n minus 2, which is pretty cool. All right, so what we want to do is look at also geometric sequences. And what is a geometric sequence? It's similar to arithmetic sequence, but to get subsequent terms, instead of adding the same number, you actually multiply by the same number. And you could see that actually you multiplied by 3, negative 3, sorry, to get each subsequent number. And so the geometric sequence listed here has a common ratio, we call that R, of negative 3. And the formula, the way to get the a sub n formula, okay, is, you learn this in pre-cal, you take the first term and you multiply it by the common ratio and you raise that to n minus 1. All right, so that is the formula for a sub n for geometric sequence. Now, some sequences are neither arithmetic nor geometric. So if you look at this sequence here, this is just 1 squared, 2 squared, 3 squared, 4 squared, and so on. Okay, so this is neither arithmetic or geometric. Sequences don't have to be arithmetic or geometric. They can just have some sort of pattern. This formula here, this 3n plus 1, is not geometric or arithmetic. And this formula here, this a sub n here, 2n minus 1 over 3n plus 1, is neither arithmetic or geometric. So sequences do not have to be arithmetic or geometric. They can be other things. All right. If a sequence has a finite limit as n goes to infinity, we say that that sequence converges to that limit. If a sequence does not have a finite limit as n goes to infinity, then we say that that sequence diverges. Now, a sequence might diverge because the terms are increasing without bound, or because the terms are decreasing without bound, okay, or because there is no limit as n goes to infinity, all right? So let's go ahead and look at what this means. First, we're going to do some examples. The first example says, determine whether each sequence converges or diverges. If the sequence converges, then find its limit. So what we're saying is, if we listed out all the numbers, would the sequence start to converge to some one number? And if it does, what is that number? And if it doesn't, then we will say it diverges. All right, so how do we do this? The easiest way to do it is just list some numbers. Okay, so we start listing the sequence. All right, if this doesn't work, we can always just take the limit of this a sub n, and that should also give us, right, the limit. That should also give us what the sequence converges to. So let's just look at this sequence. If we put in 1 here, we'll get 1/2 raised to the 0, and 1/2 raised to the 0 is actually just 1. Any number raised to the 0 is just 1. All right, if we put in 2 here, we'll get 1/2, and they've listed some of these for us already. If we put in 3 here, we'll have 1/2 squared, which is 1/4. If we put in 4 here, we'll have 1/2 raised to the 3rd power, which is 1/8. And we can go on. If we put in 5, we'd have 1 raised to the 16, I believe. And if we put in 6, we'd have 1 raised to 32, and 1 raised to 64, and so on. And so what is this sequence approaching? What number is it approaching? Can we tell? The bottom's going to get smaller and smaller, and the bottom's going to get bigger and bigger and bigger. So therefore, this number is going to get smaller and smaller and smaller. So this limit is actually going to be 0. So what we say is that this sequence converges to 0, right? Another way to do that, a little bit more technical way to do that would be to actually say the limit as n goes to infinity of this a sub n. So of 1/2 raised to the n minus 1. So you could do it either way. You could actually write out some numbers and see what it approaches. This way is sometimes obvious, sometimes not. Or you can take the limit of this expression. We've done this before. We did it with x's. This is just n's, really the same thing, okay? And so if we look at what's happening here, what this is equal to is the limit as n goes to infinity of technically 1 raised to the n minus 1 over 2 raised to the n minus 1. But 1 raised to anything is going to give you 1. So this is the limit as n goes to infinity of 1 over 2 to the n minus 1. And as n gets larger and larger and larger here, this will go to 0. So either way to do it, sometimes one way is easier than the other. All right, let's look at letter B. On your guided notes, letter B has this sequence 1, negative 1/2, 1/4, negative 1/8, and so on. And so let's think about what this is approaching, if it's approaching anything, if it's converging to anything. All right, so I have 1 comma negative 1/2, then 1/4, then comma negative 1/8, and I could keep on going with this. So this is n equals 1, this is n equals 2, this is n equals 3, this is n equals 4. If I had n equals 5, this would be 1 over 16. If I had n equals 6, all right, this would be negative 1 over 32. What is this number approaching, if anything? What's an easy way to do this? It seems like it might be 0, okay? Let's look at this. Let's graph this. Maybe graphing this will help. If I graph this, what I see is when n is equal to 1, I graph 1. When n is equal to 2, okay, so if this is 1 and this is negative 1, I'll graph negative 1/2. When n is equal to 3, I'll graph 1/4 because it's half of this distance. When n is equal to 4, I'll graph 1/2 of this 1/4 distance, but it's negative. Okay, then n is equal to 5, I'll graph half of that distance. Okay, and do you see what's happening is I'm going to go back and forth on this until this a sub n approaches 0. So this answer, this sequence also converges to 0. Okay. Another way to do that would have been to take the limit of this. So I could have done the limit as n goes to infinity of negative 1/2 n minus 1. Okay, that's the same thing as a limit as n goes to infinity of negative 1 raised to the n minus 1 over 2 to the n minus 1. I don't know if this will be helpful. What this does is this says the sequence will alternate positive, negative, positive, negative, positive, negative. Right here, what happens is this thing goes to infinity. Okay, so this will be negative 1, positive 1, negative 1, positive 1. But it stays constant, but it's negative, changes negative and positive. This down here will go to infinity. So this number here gets bigger and bigger and bigger and bigger, while this just alternates between negative and positive. And that was a little harder to tell, but that also goes to 0. All right, so there are different ways to do these problems. Sometimes one is easier than the other. Sometimes if you just write out the numbers, you can find the answer. Sometimes taking the limit as an expression gives you the answer, and sometimes graphing gives you the answer. Let's look at this problem right here, this 3/5 raised to the n. Okay, let me go ahead. I like to do this method first, but this method isn't always the best way. I like to just fill in the blanks. Okay, if I put 3/5, if I put 1 here, I get 3/5 of the first blank. My second blank is going to be 3/5 squared. My third blank is 3/5 third. My fourth blank is 3/5 of the fourth. What is happening here? What's happening is that I'm multiplying by 3/5 each time, right? I'm taking 3/5 of the answer before. And what does this approach? Well, this is a geometric sequence. I can see that. It's a geometric sequence. And so actually what's going to happen is the number is going to get smaller and smaller and smaller, right? Because I'm going to take 3/5 of the number before, and I'll take 3/5 of that, and I'll take 3/5 of that. So what happens is this number gets smaller and smaller and smaller, and it will approach 0. So what we can say is that if this ratio, this common ratio is 3/5 of a geometric sequence, if this common ratio is less than 1, okay, it could be negative too. If the absolute value of it is less than 1, then you're always taking a part of the a sub n before. And so because of that, you will converge, okay, to 0 for geometric sequences. Now, make sure you understand, this says the sequence converges to 0, not that the series converges to 0, okay? And that might be not clear at this time, but the series does not necessarily converge to 0. The sequence means if there are commas in between here, these numbers will eventually converge to 0. But the series is a different animal, and we'll talk about that in a few minutes. All right, let's look at letter D here. Letter D says I've got 5/3 raised to the n. Okay, now how is this going to be different? Well, if I have 5/3 raised to the n, what I'm doing is I'm multiplying by 5/3 each time, right? So let's look at this problem. This would be 5/3 in the first blank, okay? Then 5/3 squared in the second blank. Then 5/3 raised to a third in this third blank. And what I'm doing each time is I'm actually multiplying by 5/3, right? I'm multiplying by 5/3. But if you multiply by 5/3, 5/3 is a number greater than 1. So I'm multiplying by a number greater than 1 each time. So if this makes any sense, I'm going to get bigger and bigger and bigger and bigger, okay? So this thing is actually going to approach infinity. So for a geometric sequence, all right, if your ratio is bigger than 1, what's going to happen is your number's going to get larger and larger and larger. And this sequence, what we call the sequence, will diverge. Okay, we didn't say the series diverges. The sequence, okay, is actually going to diverge. Maybe diverges, the geometric sequence diverges. Now, what you need to know is the series in this case actually also diverges. Not in this case though, but in this case it does. But we'll talk about series later. All right, let's go to the next worksheet or the next page, which has this problem here. A sub n is equal to Sn, all right? Does this sequence converge or diverge? Let's look at it. If n is equal to 1, I get sine 1. If n is equal to 2, I'd have sine 2. If n is equal to 3, I have sine 3. If n is equal to 4, I'll have sine 4. Is this going to diverge or converge? Well, let's think about, there's different ways to do this. This is interesting because this really doesn't help me because I don't know the value of sine 1, sine 2, sine 3, sine 4. So what I do is I always approach this. There's three ways to approach it. First is just to write out the blanks. If that's not helpful, you could also just do the limit as n goes to infinity of sine of n. Okay, what's going to happen here? This is not so obvious, but sine actually goes between -1 and 1. So actually the easiest way to figure out what this sequence converges to is actually just graph this. If you graph sine, okay, what you're going to get is a curve that goes between 1 and -1, right? Does it approach any one number? That's how we know it converges, okay? Does the y value approach any one number as this goes to infinity? No, it doesn't. It actually oscillates between -1 and 1, all the numbers between -1 and 1, right? So what we say here is since this sequence does not converge to any one number, then this sequence actually diverges. So let me make that clear. This sequence diverges, okay? Let's look at letter F. Letter F says, okay, I have this problem here, this a sub n. Does this sequence diverge or converge? Well, I could put in blanks, n equals 1, n equals 2, n equals 3. Okay, put some numbers in. If I put in 1, I'll have 5 over 4. If I put in 2, I'll have 8 over 9. If I put in 3, I'll have 11 over 14. I'm not sure that this is very helpful to me. Okay, remember the second method we could use. The second method we could use is just take the limit. So let me actually just take the limit as n goes to infinity of this expression, 3n plus 2 over 5n minus 1. That's another way to find if this sequence converges or diverges. What is it? And if it converges, what does it converge to? Actually, I know how to do this because the powers here of the leading terms are the same. So this answer is the ratio of the coefficients of the leading terms. And so this answer is 3/5. So the answer to letter F is that this sequence actually converges to 3/5. All right, so remember there's three ways to do each of these problems. One way might be easier than the other. One is just to list out all the numbers. The second is actually to take the limit as n goes to infinity of this expression. And the third is to graph it out. And one of those is going to help you find the answer to whether a sequence converges or diverges. Okay, again, let me clarify that we're talking about sequences here and not series. All right, let's look at this problem here. This a sub n is equal to 3 plus -1 or +1. Okay, if n is equal to 1, then what I'll have here is 3 minus 1, which would be 2. If n is equal to 2, I'll have 3 plus 1, which is 4. If n is equal to 3, I'll have 3 minus 1, which is 2. If n is equal to 4, I'll have 3 plus 1, which is 4. So what's happening here? This thing is going to alternate, right? Try another one. N equals 5, this is going to be 2. N equals 6, this is going to be 4. This is going to alternate between 2 and 4. So question, does this sequence converge to one number? No, it does not. So actually we say that this sequence diverges. All right, does not converge to any one number. All right, let's look at this problem here. Again, I could do blanks, n equals 1, n equals 2, n equals 3, n equals 4, and what I'll get is ln of 1 over 1, which is 0, right? Ln of 2 over 2, ln of 3 over 3, ln of 4 over 4. Well, I was doing well with ln of 1, but I really don't know ln of 2, ln of 3, ln of 4. So remember, this is just one way to do the problem. The second way to do the problem is actually to take the limit of this expression to find that if the sequence converges or diverges. If I take the limit of this, is this helpful? Well, if I plug in infinity, I'll get infinity over infinity, right? And so I could invoke L'Hopital's. Okay, so if I invoke L'Hopital's, okay, I put an LH there. What I'll do is this L, remember, stands for limit, so this is a limit as n goes to infinity. The derivative of ln of n is 1 over n. The derivative of n is 1. So what I get is a limit as n goes to infinity of 1 over n. And as n gets larger and larger and larger, this is equal to 0. And so what we know is that this sequence converges to 0. Another way to have done this is to see that right here you have small over big. Okay, that's another way to know that this is 0 without doing L'Hopital's. Okay, let's look at this problem here. Again, one way to do it is actually just to write out the numbers, okay? But I want to just look at this and say, you know what, I think I could just take the limit as n goes to infinity here of n plus 1 factorial over n plus 3 factorial. And this is very similar to our warm-up. Okay, if I could figure out what the limit of this problem is, then that is what this sequence converges to, or maybe it diverges. So what I want to do is actually simplify here. Remember, I know that n plus 3 is actually n plus 3 factorial is actually n plus 3 times n plus, subtract 1 from this, so it's going to be n plus 2, subtract 1 from this, and what's going to happen is this is going to match up with the top here, factorial. And the top here, I know, is n plus 1 factorial. I mean, if you wanted to write out more, you could. If you wanted to write out more, you could see that the next term here would be n. Okay, the next term here would be n. The next term here would be n minus 1. Okay, the next term here would be n minus 1. You could write out more terms, but what happens is they always match up, and these are going to cancel out to 1. So what you get here is a limit as n goes to infinity of 1 over n plus 3 times n plus 2. Okay, and what is the answer to that? Well, n is going to get larger and larger and larger. The numerator is going to hold at 1, so this answer will be 0. So we say that this sequence converges to 0. All right, let's do some different problems. Okay, let's talk about series now. All right, now we know how to do sequences. Let's talk about series. Now, what does it mean for an infinite series to converge or diverge? That is different from a sequence. All right, we're talking about series now. We say that an infinite series converges if the sequence of partial sums converges to some number s. Okay, now that's a lot to think about. Okay, but what we need to know is that an infinite series converges if its sequence of partial sums converges. Okay, if its sequence of partial sums diverges, then the series diverges. All right, so let's look at what partial sums is. All right, if we have a series like this, and what is a series? A series is a sequence with plus signs in between. All right, so now we don't have commas anymore, we have plus signs. All right, and what we're going to say is, does this converge or does this series diverge? All right, so what we need first is partial sums. So what partial sums are is it's the sum of the first term, so that's then the sum of the first two terms, then the sum of the first three terms, okay, then the sum of the first four terms, and so on. So if I made some more terms here, it'd be 3 plus 5 plus 7. I can see that this is an arithmetic series, we're just adding 2. So this would be plus 9, plus 11, and so on. So S1 would just be the sum of the first term, so that's 3. S2 would be the sum of the first two terms, so that's 3 plus 5, which is 8. S3 would be the sum of the first three terms, so that's 3 plus 5 plus 7, which is 15. Okay, you see how this works? S4 would be the sum of the first four terms, so that's going to be 3 plus 5 plus 7 plus 9, and that's going to be 24. And S5 is going to be the sum of the first five terms, 3 plus 5 plus 7 plus 9 plus 11, and that's going to be 35. And of course, you can go on infinitely. Okay, and what we're going to do is we're going to take these partial sums and turn them into a sequence. All right, so the sequence of partial sums will be 3, 8, 15, 24, 35, and then we look at this sequence and we decide, does this sequence converge or diverge? Okay, so we go back to like the problems we did before. Okay, once we find the partial sums, then we say, does this sequence converge or diverge? And we can see that this sequence is actually approaching infinity. So because this sequence of partial sums diverges, then what we're going to say here is that the series diverges. Okay, so let me make that clear. What do we notice about the results? We notice that the sequence of partial sums diverges or increases without bound. Okay, therefore the series. Okay, this is the same as saying it diverges. Okay, so therefore this series diverges. Okay, so that's when we know series diverges. Okay, just because just because the sequence of partial sums diverges, that's why the series diverges. Okay, and let's think about anytime we have an arithmetic series. Okay, anytime we have an arithmetic series, this series is going to diverge. So all arithmetic series will diverge. Okay, and so because of that, that's pretty boring. So it's not really likely that I'll ask you if an arithmetic series would diverge or converge. So we're pretty much done with the arithmetic series here. All right, let's look at this series here. The question is, if you look at this series here, does this series converge or diverge? All right, well, let's think about how we realize if a series converges or diverges. We need its partial sums. We need to make its partial sums into a sequence. All right, so let's find the first 10 partial sums. So S1 is going to be 3 halves. Okay, S2 is going to be 3 halves plus 3 fourths. Okay, and we can put that into our calculator. So if I pull, if I pull my calculator over, okay, I can say, well, what's 3 halves, which is 1.5, okay, plus 0.75, and we can see that's 2.25, and I can do S3, and S3 is going to be 3 halves plus 3 fourths plus 3 eighths, oops, that's a plus sign, and S4 I can see is 3 halves plus 3 fourths plus 3 eighths plus 3 sixteenths, and S5 is going to be the first 5 terms here. So that's going to be 3 halves plus 3 fourths plus 3 eighths plus 3 sixteenths plus 3 over 32 and so on. Okay, so let me go ahead and write these down. We'll figure out what these values are. S10. All right, so let's go back to my calculator. For S3, it's 2.25 plus 3 eighths. So plus 3 divided by 8, and that's going to be 2.625. Okay, then this 2.625 is right here. So I'm going to add that with 3 sixteenths to get S4. So I get 2.8125 here. And I'm going to add that number with 3 over 32nd to get S5. 2.90625. And S6 is going to be this number plus 3 over 64. 2.953. And then I'm going to add this number with, see, that was 337, 3 over 128. It's going to be 2.976. And I'm going to go ahead and fill in the rest of these, and you can verify it on your own. Okay, S8 is going to be 2.988, S9 is going to be 2.994, and finally S10, 2.997. Do you see what these numbers are approaching? 1.5, then 2.25, then 2.625, 2.8125, 2.90625, 2.953, 2.976, 2.988, 2.994, and 2.997. What is this sequence of partial sums approaching? Yeah, it's approaching 3, right? So what we say is this sequence of partial sums converges to 3. So the sequence of partial sums converges to 3. So therefore, this series actually also converges to 3. Okay. Now this is kind of interesting because if we look at this very carefully, what we can see is that this series up here is actually a special series. It's a geometric series. You can see that this is a geometric series, okay, with a common ratio of 1/2. Okay, to get to each term, we multiply by 1/2. And if you remember from pre-calculus, there is a formula for the sum of an infinite geometric series. Do you remember that? The sum of an infinite geometric series had this formula, a1 over 1 minus r. Your a1 is just your first term. This is your a1. Remember, this is your a2. This is your a3. Okay, so your a1 is actually 3/2. 1 minus r, your r is your common ratio here, 1/2. Okay, this is really equal to 3/2 over 1/2. And dividing fractions, easy as pie, flip the second and multiply. What we'll get here is that this sum is actually 3, and that was the same thing we got here. Okay, so what the series converges to is actually also the sum, okay, of an infinite series. All right, so that's kind of interesting. If you remember though, in pre-calc, this only worked if your r was less than 1/2. If your absolute value of r was less than 1, that's the only time that this formula worked. All right, question. The area in your approximation is the difference between the actual sum of the infinite series and the sum of the terms that you added. What is the error in this approximation? So in calculus, error is just actual value minus approximation. This is your approximation right here. This is your actual here. So this is going to be 3 minus 2.997, and this answer is going to be 0.003. The nice thing about calculus is you never have to worry about is your error positive or negative. it's always just positive. We always just take the absolute value. How could we make this error smaller? The answer is always the same for calculus. How do you make errors smaller? You increase the number of terms. And what about other geometric series? Do all geometric series converge? And we talked about that. Okay, well, if you multiply this by a number larger than 1 or equal to 1, what's going to happen is that this sequence would diverge, and the sequence of partial sums would also diverge. So really, for geometric series will converge only if the absolute value of r is less than 1. Okay, if the absolute value of r is equal to or less than 1 or greater than 1, sorry, then this geometric series will diverge. So let's look a little bit closer at this series that we had here. Let me write the series again. I think the series was the sum of 3 over 2n as n equals 1 to infinity. All right, so if we look at this closely, okay, we could have seen that another way to write this would be the sum as n equals 1 to infinity of 3 times 1 over 2 raised to the n power. It's actually the same thing here. And so this is in that geometric series formula, kind of. This is a, this is 1/2, which is like your r. Okay, so this is r raised to the n. Okay. And if we looked at this, then what we can see is this is a geometric series. This is your r. And because of that, we can use this formula to figure out the sum of the geometric series, or what the geometric series converges to. So this would be a1 over 1 minus r. Well, what's your a1 here? You actually have to plug in n equals 1 here. So if I plug in n equals 1 here, okay, I'll get 3/2. So that's my a1. So this is equal to 3/2 over 1 minus, and I figured out that this was my r, right? You multiply by 1/2 each time. And again, I've already done this, but this answer is actually 3. Okay, something important to notice. When r is less than 1, when r is less than 1, so look at this. When r is less than 1, okay, then you can use this formula, actually the absolute value of r. So r can be negative also, okay? If it's negative 1/2, this formula would also work, okay? So when r is less than 1, you can plug it into this formula and figure out what your series converges to, okay? But when r is greater than 1, okay, this formula doesn't work, and that makes a lot of sense. But why doesn't this formula work when r is equal to 1? Okay, so I want to take some time to talk about that right now. If I had a geometric series that was this formula here, okay, this is a geometric series. Why is it a geometric series? Because let me put in n equals 1, n equals 2, n equals 3. If I put in n equals 1, okay, this would be 0. So the first thing in the blank here would be 3. If I put in n equals 2, okay, this would be 1. So then this would also be 3. If n is equal to 3, okay, this would also be 3. What about when n is equal to 4? If n is equal to 4, this is 1. This is also going to be equal to 3. Okay, so this is a series. This sigma here means addition. So this is a series. Okay, and so what I have here is a geometric series. Okay, and each term, if I look at the sequence here, each term I multiply by 1. Okay, so my r here is 1. All right, so what I have here is an infinite geometric series with r equal to 1. Okay, according to my formula, I said that when absolute value of r is greater than or equal to 1, okay, that this geometric series diverges. Well, let me make sure. Its geometric series diverges, okay? But this is kind of interesting. This is why it's important to understand the difference between sequences and series, okay? This sequence here, look at this sequence. This sequence is 3, 3, 3, 3. Does this sequence converge or diverge? This sequence actually converges to 3, okay? But let's look at this series. This series is 3 plus 3 plus 3 plus 3, okay? This series actually diverges, okay? Because its sequence of partial sums, so 3, 3, and then 6, right? The sequence of partial sums, 9, okay, then 12, then 15, then 18, and so on. This sequence of partial sums is going to diverge, so therefore this series actually diverges, which is interesting, okay, because what we know here is that the sequence can converge while the series diverges. All right, so make sure you understand that just because the sequence converges does not mean that the series is going to converge also. All right, let's look at another problem. This problem right here. Okay, given this series right here, we want to find the first 5 terms of the sequence of partial sums to figure out if this series converges or diverges. All right, so S1 is going to be equal to 3 halves, just the first term. S2 is going to be 3 halves plus 9/4, so I can pull my calculator out and do 3 halves, which is 1.5, right? Oops. 1.5 plus 9/4. Okay, I get 3.75, and this right here is 1.5. If I do S3, okay, I'm going to add the first 3 terms together, so I'm going to take this number and I'm going to add it with 27 divided by 8. Get 7.125. If I do S4, I'm going to add this number with 81 divided by 16. I'll have 12.1875, and S5 will be this number plus 243 over 32. This number will be 19.781. All right, so let's look at the sequence of partial sums. The sequence of partial sums here is 1.5, oops, 1.5, then 3.75, then 7.125, then 12.1875, then 19.781, okay? Does this sequence of partial sums converge or diverge? It actually increases without bound, right? So what we notice is that the sequence of partial sums diverges, okay, increases without bound. And because the sequence of partial sums diverges, then what we know is that this series, therefore, this series actually also diverges, okay? So remember, we learned this formula. Could we use this formula to figure out what this series converges to? No, not in this situation. Why not? Well, first of all, is this even a geometric sequence or geometric series? What did I multiply each time to get the next term? 3 halves, right? So what this common ratio is equal to 3 halves. Is the absolute value of this less than 1? Because that's the only time that you can use this formula. No, this is actually greater than 1. So because this is not true, because r is actually greater than 1, okay, we cannot use this formula to figure out if this is true or not. So if you did use this formula, you might get an answer, okay? You actually will get an answer, okay? I mean, I could do it. You get an answer, but that answer is wrong. It's not allowed to use this formula for figuring out what this geometric series converges to, because this geometric series is not going to converge. All right, so make sure you understand when you can use this formula. Okay. Let's look at this. What if a series isn't geometric? So today we looked at geometric series and arithmetic series, but what if a series isn't geometric? Looking at the first few terms of the sequence of partial sums may not help us. Okay, so what we're going to do in subsequent lessons is to, besides geometric series, okay, figuring out if series converge or diverges. So I'm going to give you a series. I'm going to ask you, does this series converge or diverge? If it's a geometric series, then all you have to do is figure out your R, find your R. Okay, if your R is less than 1, then you would say that the series converges. If your R is greater than or equal to 1, then you would say that the geometric series diverges. But if it's not a geometric series, we're going to learn other tests, several other tests, to figure out if a series converges or diverges.